Hi, welcome to 10.5. So there's some important vocabulary here. The only one you probably are not familiar with is entropy. Just think of that as randomness or disorder. We'll cover that in 16.2 in a little more depth, but just focus on that for right now. Intro questions, just for you to kind of get in the mood of section 10.5. And so, let's begin. So many of you know phase changes as changing from one state of matter to another. There's a nice diagram here, which I'll highlight here, and the main focus is you have this understanding often from the macroscopic size. You see an ice cube melt, it turns to steam, and so on. But I want you to focus in on what the molecules will be doing. So the solid has them nice, packed, and orderly. The liquid have them very close together but less orderly, and a gas, as you can see, they're further apart, moving all over the place. In each of these, as these are melting, what you want to be keeping in mind is that they are also losing or gaining energy, and we'll talk about that a little bit later. It takes a removal or an addition of energy for these things to happen. If we're talking about going from vaporizing our liquid to a gas, that's the molar enthalpy of vaporization. Fusion is a fancy name for freezing. Okay, so freezing and vaporization are going to be our main focus. Sublimation, deposition, that's not really happening too many things with too many sources. These values depend on the intermolecular forces holding these particles together. We're often just going to talk about water, but any of these substances have a molar enthalpy of vaporization or fusion. So I want to bring your attention to this diagram down here because it shows heat energy is always constantly increasing as we go from left to right as we're going from a solid to a gas. Many of you are very comfortable with that, as temperature will also increase. But what might not be clear is that as it's melting or as it's freezing, it's not changing temperature, as you see, but we still need to add energy. So energy is being added or taken away in the case of freezing or condensing in order to go from a solid to a liquid or a liquid to a gas. So energy is added as something melts, for instance, ice melting to liquid water. The temperature does not increase, but we need to add energy. This is the heat of fusion. This is the heat of vaporization. Now, when we often think of going from liquid to a gas, it will be positive. Again, solid to liquid, it will be positive. How much energy does it take how much energy has to be removed to freeze? The same amount. How much energy has to be removed to condense it? The same amount. So it's the same amount either way, only it's a positive value going up from solid to liquid. It's positive. Going from a gas down to a solid, it's a negative value. Okay? So that's what we're going to look at in this section mostly. So let's look at our next slide. Heat of vaporization and fusion. When a substance melts, it's endothermic. Remember, endothermic is you're adding energy. So these are all endothermic. When it condenses or freezes, it's exothermic. It's removing energy. So this often confuses students because students think exothermic as being like a fire, being hot. And so it's really confusing. We go, well, how do we release heat but it go from water to ice? And that's because it's going to warm the surroundings. When you freeze water, you're actually warming the surroundings, removing the heat from the liquid. What's easier to see is as you go from ice to water, you're adding energy. So you're going to need to take it from somewhere. So when you hold a piece of ice, how does your hand feel? Hopefully you said cold, otherwise you might have some nerve damage. It should have felt cold, and so when it feels cold, it's because it's taking heat from your hand and becoming liquid water. Same goes for evaporation. This is why when you sweat, the liquid water on your skin evaporates, taking energy from your body, making you feel actually cooler. Okay? So these phase changes require heat to be transferred from something more random to something less random. If we zoom into our ice over here, our ice is very ordered. It actually forms hexagons. Water, just a tight clump. Water vapor, it's all over the place. So that's why it's important that we go from higher temperature to lower temperature. We can also consider that to be higher entropy to lower entropy. Again, entropy being randomness. So entropy, again, is this randomness. This will make a little more sense, I think, when we get to chapter 16.2. But what we can show is that entropy, this randomness, increases as we go from solid to liquid to gas. And as we get higher up with entropy, the gas is going to have the highest entropy, liquid, and then solid. And we can see that at these different phase changes, going from melting and boiling, the entropy increases rapidly. Each substance does this to a certain different degree. Oxygen has a pretty low heat of fusion. Ethyl alcohol, quite high, because there's more attractive forces. Oxygen and nitrogen are nonpolar, if you remember back in the day. Water being polar, ethyl alcohol being polar. And these being metals, these are already solids, so it's going to take a lot of energy to fuse them. And you can see what really has the increase is, oh, I'm sorry, ignore that. We'll erase that. What really has the increase is the heat of vaporization. We see that it's much higher for a metal because it's really hard to vaporize a metal. But even look at water. Water almost has the same heat of vaporization needed as silver does. But silver does it at 2193, water does it at 100. Why? Well, that has to do with heat capacity. Okay, so that actually refers back to a previous section. But each of this has to do with the intermolecular forces. So let's look at how we can solve some of these math problems. So you recognize there's a mass and energy involved. You're going to be using conversion factors, either mole enthalpy of fusion or vaporization. It might be given, it might not. It's in the section. And again, we want to do this, that if you're given grams, it might be 2 steps, moles 1 step, energy 2 or 3 steps, depending if they're talking about kilojoules to joules or joules to kilojoules. So again, we're using these enthalpies of vaporization as conversion factors. You know your molar masses, you know your kilos to whatever. And again, however many sig figs you start with, you end with. Start with, end with. Again, this should feel very familiar. It's just we get a different conversion factor. It's like changing out bread or changing out meat or changing out cheese in a sandwich. It shouldn't blow your mind that we're changing one thing from what we've done many times before. So let's look at some examples of this. Find the mass of liquid water requiring to boil, energy on boiling. So this is as it goes from a liquid to a gas, not changing in temperature, just remaining the same. So we always start with what we're given, our 5.23 times 10 to the fourth kilojoules. And I'm trying to find, might go over here a little bit, grams of water. So I have kilojoules on top, I need kilojoules on the bottom. Anything that I've been dealing with here has moles of water here. It's the only thing I've seen that has kilojoules involved. And whatever's on top goes on the bottom. And if I'm trying to find grams, well, I know I can relate grams to moles with our molar mass. That's 18.02. You'll get familiar with that one a lot so far. 1. And per mole, I have 40.79 kilojoules. All my units are canceling out. I do my math, and I get 2.31 times 10 to the fourth grams of water, provided that much energy was used to vaporize that much water. So again, it looks much like we've seen before. So look at the next one. how much energy is absorbed when 16.3 grams of ice melts? So molar enthalpy of fusion is much less than our heat of vaporization because of those intermolecular forces. But again, I'm starting off with 16.3 grams of water. Ice is still water, just be a solid. And I'm curious about how much energy, so kilojoules, is absorbed. So whatever I start with, I need to have my grams of water. And that's, of course, to moles of water. What's on top goes on the bottom, as we've been doing all year long. And moles goes to kilojoules, because here's my conversion factor right here. And again, many students go, well, it can't go on the top, can't go on the bottom. It can go wherever it needs to go. And it's 6.009 kilojoules for each mole. And again, we have our 18.02 grams for 1 mole. Do my little multiplication, and I have 5.44 kilojoules, because I start with 3 sig figs, I end with 3 sig figs, to melt 16.3 grams of ice. Alright, now it's your turn to try these. Take a moment, do those, come back and see if you got them right, if you had trouble getting the answer. So here we go. So we're starting off with our 783 grams of course, water. We're trying to find how much kilojoules is going to be released. So again, we need to have it in moles with our 18.02 grams of water equal to our 1 mole of water. And again, this is going to be condensing, so I see that this has to do with vaporization. So that means that I have 40.79 kilojoules for every 1 mole of water. So again, units canceling. My answer, 3 significant figures, because that's what I'm starting with, so 1770, which is the same as this here. Alright, so looking at the next one, massive ice melting if it absorbs so much energy. So the idea is we're looking at starting off with an amount of energy and looking for grams of water of how much that energy absorbed. So again, kilojoules, making sure you know which one you're talking about. Since we're dealing with ice, that would be our heat of fusion, which is our 6.009 kilojoules per mole. And again, what's on top goes on the bottom, considering units. And we know that's our common 18.02 grams of water. So, do my multiplication and division, start off with 3 sig figs, we end off with 3, and that's where we get our 3.75 times 10 to the 9th grams. It's your turn to do the review questions. Be sure to answer these completely and come in with any kind of questions you might have. See you soon.